right, these are the answers to the first review. First one says that if we let x go to infinity, what will this go to? And what you always want to do is look at the largest degree here and the largest degree term here. None of the other degrees matter. None of the other terms matter. I've got 3x to the third on the top and a negative 1x to the third on the bottom. They're the same degrees, so they're the same kind of magnitude. So therefore, as x gets bigger and bigger, this is going to want to gravitate to the ratio of that, which means this limit will go to negative 3. So in other words, over time, if you were to look at this graph, it would just bottom out and start to level off at that horizontal asymptote of negative 3. For the next one, we have this function here, and we're asked what are all the x coordinates of points of inflection. So we want to take the first derivative of this, which if the 7 comes down, we'll cancel that 7. Will give us 5x to the 6th plus 24x to the 5th plus 30x to the 4th plus 1. Then we're going to take the second derivative, which will be 30x to the 5th plus 120x to the 4th plus 120x cubed. We're going to go ahead and take an x cubed. We're going to set it equal to 0, and we're going to take a 30x cubed out, which will give us x squared plus 4x plus 4 left over. And that will factor into x plus 2, or x plus 2 squared. All right, so our possible points of inflection would be x equals 0 and x equal negative 2. So now what we do is we come over here, put a negative 2, 0. We're going to test out our second derivative. If I put something less than negative 2, say negative 10, into the second derivative, I'm going to get a negative, very large negative number here, and then a positive and then a negative here. I'm going to end up with a negative value there. That means we are concave down. If I were to put negative 1 in here, I'm going to get negative 30 plus 120 minus 120. That's going to give us a positive, so we're concave up in that spot. And if I were to put something bigger than 0, say 10 into this, I'm going to get positive, 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 still positive. We're going to be concave up. So we do have a point of inflection, right? Point of inflection at x equal negative 2, but we do not have one at 0 because we did not see a switch in the second derivative. This here says, suppose we have a function twice differentiable, and we are guaranteed that there's a derivative value of 0 somewhere between a and b. What would that guarantee? Well, first off, if we're guaranteed to have a horizontal tangent, that's because the average rate of change between a and b would have to have been 0 as well, which means f of a and e has to equal f of b. That's the only way you can be guaranteed of something like that. Okay. Now, would we have to have a relative extremum or a point of inflection? Not necessarily. If it's just a horizontal line between a and b, there's a guarantee of a derivative somewhere equal to 0, but wouldn't necessarily give us an extreme, wouldn't necessarily give us a point of inflection. So these two things don't have to be true. The point of inflection is the one that's least true. If you thought about the b or 2 being there because it might give you a high or a low there, you know, that one I would say I'd be happy with if you saw that one, but I wouldn't be so happy if you chose 3, right? Just to kind of differentiate those two. Next question says, what are all the values of x for which this is concave down? So we're going to take the first derivative, which is 3x squared minus 12x, and then we're going to take the second derivative. And try to find those points of inflection. 6x minus 12, set that equal to 0. Solve it, we get x equal to 2. Okay, put 2 down. If I pick something before 2, say 0, I put it into the second derivative, I'm going to get a negative. If I pick something after 2, say 10, put it in, I'm going to get a positive. Okay, so we're concave down before 2 and concave up after 2. So when are we concave down? From negative infinity to 2. And that's because that's where the second derivative is negative. For what value of k will this have a relative maximum of x equal 4? So this is kind of a trickier problem. We're going to take the derivative to start with, and we're going to have to use quotient rules. So that's bottom times derivative of the top, which will just be 8, minus top times derivative of the bottom, which is 2x, over bottom squared, which will be x to the 4th. All right? And if we work this out, this is 8x squared minus 16x squared. So that'll be a negative 8x squared on the top. And then a minus 2x times k will be a minus 2kx, right? All over x to the fourth. All right, now what they want is for this to be a relative maximum of x equal 4. So what that means is if I were to put 4 in for x into this derivative, I should get 0. So if I were to go negative 8 times 4 squared minus 2k times 4 over 4 to the fourth, that should give me 0. Now, if I multiply by this 4 to the fourth, it'll still be 0, right? So this top here, this negative 8 times 4 squared minus 2 times k times 4, will give me negative 8 times 16, which I'll just do real quick, negative 128 minus 8k equals 0. If you add 8k over and divide, we end up with k equal to negative 16. So again, what did we do? We took the derivative using quotient rule, we set it equal to 0, and we said that had to equal 0 when x was 4. Put 4 in, that's what we get. All right, this one here says let f be a differentiable function with f of 0 equal 11, f prime 0 equal 17. Use the tangent line. So as soon as we see tangent line, all right, we're going to think point and slope. The point here is 0, 11. The slope is 17. So we're going to have y minus 11 equals 17 times x minus 0. That's our equation of our tangent. They want us to use it to figure out an approximate value of f of 0.05. So we're going to put that 0.05 in for x. And what's going to happen is we're going to have y equal to 11 plus 17 times 0.05. Okay? And if we do that, we should get 11.85 as our approximation. So that's building the tangent line like we've done so many times, plugging this value in to get an approximation. Then the second part says if the graph has a second derivative greater than 0. So a second derivative greater than 0 means that we're concave up. So if the graph is concave up and we're approximating, say, right here, then that tangent line that we just used to get this value, say, over here, happens to be under the actual value. So when it says, is our estimate an overestimate or an underestimate, our estimate is less than this, so it would be an underestimate. And we would say that tangent lines are under concave up graphs. And that would let the grader know that we understand that connection. All right, last section here. We said if f double prime is this and we have these critical numbers, can we figure out if they're relative max mins or something else? So what that means is you're going to take the second derivative of each one. If I take the second derivative of negative 2, I'm going to get negative 8 plus 4, I'm going to get a negative 4. Now, the fact that I got a negative means that it's concave down at that part. But we said that negative 2 is a critical point where the derivative would be 0. So that must mean that x equal negative 2 is a relative maximum. Because the second derivative at that point is negative, which means it's concave down, puts us at the top of that. Same thing for 1. If I do second derivative at 1, I'm going to get 1 minus 2, which is negative 1. Still negative, therefore still a relative maximum. And if I do this for positive 2, I'm going to get 8 minus 4, which is positive 4. So now I get a positive. That means we're concave up now. And if that's the critical point of the graph where we're concave up, then we must have a relative minimum there. It's just an alternative to finding relative max and relative minimum. This one wants us to find horizontal asymptotes. What that means is they want us to find the limit as x goes to infinity and the limit as x goes to negative infinity. So the infinity one's easy enough. If I let it go to infinity, I have 1x here, and the square root of 4x squared would be 2x. 1x over 2x would give me 1/2. Okay? But if I go to negative infinity, the top will go to like a negative infinity, right? But the bottom, the negative will go away, because once you square it, it turns it positive, and then the square root will keep it positive. What that means is that as you go to negative infinity, your graph's going to go to negative 1/2. It's the same idea. We ignore the -5, we ignore the 3. Those things won't matter. All that matters are the leading terms. But because of the squaring first and then square rooting, it will lose the negative on the negative side, and that will take us to a different spot. So it's an example of a graph that kind of looks like this, where it's heading off to 1/2 on the positive end, but to -1/2 on the negative end. Does the mean value theorem apply to this on the interval 2 to 4? No, it's not continuous. How do I know it's not continuous? F of 2 doesn't exist. Or I should say is undefined. Put 2 in, square root of -1, you get that I unit. Doesn't work. All right, now we've got a graph of velocity. Find all the values t where a relative minimum is located. So we're talking, since this is like a derivative graph, a relative minimum is where our derivative switches from negative to positive. We go from decreasing to increasing. So this graph goes from negative to positive at -3, and then again at +4. Is the speed increasing or decreasing at t = 3? So at t = 3, you can see that that's the part of the graph that's moving away from 0. So we could say that it's increasing because of that moving away from 0. We also know this because the velocity at that time is negative and the acceleration is negative. So signs agree, therefore our speed is increasing. Approximately, what are the inflection points located? So an inflection point for our graph would be where our derivative switches from increasing to decreasing. So that's approximately -2 point something. Let's say -2.2 or something like that. Or where it switches from decreasing to increasing, which appears to be at 0. Again at 2. And then later on at like 3.5-ish. Again, those decimals we aren't going to, the AP does a good job of defining those, so don't panic about that. What interval is the concave down? We're going to be concave down when our derivative is decreasing. If my derivative is decreasing, then my original function will be concave down. This derivative is decreasing at what we thought was about -2.2 to 0, and then it's decreasing again from 2 to about 3.5. So it's a good range of different things from old things that we've been doing right now. Hopefully that felt okay.